YouTube stream as well, so everything is now rolling, as they say. So we're gonna go over binary subtraction today. That's mostly the topic of today, and I'm hoping everybody has a restful weekend, even though it's kind of hot and smoky and the sun is all kind of funky and all that. But otherwise, I hope you guys got a relaxing weekend to rest, and also a little bit of time to review the content, the material, because everything that we do today is built upon things that we have done already. So that makes it kind of important to kind of review the content of last week's lecture. I'm just looking at the time. We got about 1 minute and 20 seconds to go. All right. So today's lab is carry look ahead adder part 1. So my advice is to get started with it like early, because it's due on the 10th, which is 2 days later. So you don't really have a whole lot of time to work on it, even though you do have some time. But it's probably a good idea to get a head start on this one. Just because from experience, I know the questions, as much as I try to make the questions clear, they may be slightly confusing to certain people. So you might want to get a head start on that one, after the lecture. And then today's main lecture is going to be on binary number subtraction, which is a short module by itself, but that's only because it is built upon concepts that we have already learned in binary number addition. So that's what we'll be talking about today. All right, so it is 7 o'clock. I'm getting started with the lecture. As I talked about a little bit earlier, we're going to talk about binary number subtraction today. So let's go ahead and take a look at that module. And I also strongly recommend everybody to open up the module on your own browser. So this way, when I go between several screens, yours can stay put on a particular portion of the content. So that way, it's less transition for you from your perspective. All right. So the first thing about subtraction is, let's try to do subtraction in base 10. Okay. This is kind of the way I do things. Is I try to bring things that are familiar to you to begin with, and then we'll extend it. We'll generalize the concept, and then we'll extend it to the base, the specific case that we want to learn, in order to understand how computers operate. All right, so I'm just going to go with the notes of or the examples that are already listed here. So we'll start with 9 minus 2. Okay, this is all in base 10. So 9 minus 2 is 7. That's hardly surprising. But the reason why we know 9 minus 2 is 7 is only because we have memorized this particular subtraction case from elementary school. I'm guessing somewhere between 1st and 2nd grade is when we learned subtraction after addition, because addition is easier to learn, subtraction is a little bit harder. All right, but we also want to know that there is a borrow of 0. Okay, so normally we say there's no borrow, but we want to kind of change the way we say that into there's a borrow, except the borrow is a 0 from the more significant digit. So now we want to talk about what is 2 minus 9. So 2 minus 9, you can probably call it -7, because if you just want to look at the value of 2 minus 9, it is -7. But it doesn't really help us, if we look at 2 minus 9 this way, it doesn't help us to perform multi-digit subtraction. So the way we want to look at it is to say 2 minus 9 has a single digit answer of 3 with a borrow of 1. Okay, so the 3 is the single digit result of 2 minus 9, but then we have a borrow from the more significant digit. So that borrow of quote unquote 1 from the more significant digit is actually borrowing a quantity of 10 from the perspective of the digit that is doing the borrowing. And that's why now we have 10, and 10 plus 2, which is 12. 12 minus 9 is, in fact, the 3. So do we have any questions about this portion of the discussion? And I'm going to get started with a kind of portable notepad. So give me a moment to set that up. All right. All right, so over here, what I'm doing is I'm just setting up the subtraction. So this is a single digit. So we got a 2, and we want to subtract 9 from the 2. And the answer is, it is a 3. This is the single digit answer to 2 minus 9. But then we also have a borrow of 1 from the next digit. So we want to kind of label these columns, okay? So I would still continue to call the first row. Oh, okay, it doesn't show up very well in the rendering. I think it's because sometimes it doesn't understand that I want to use plain text. Okay, that's fine. This is Markdown, by the way. So I'm still learning how to use Markdown. All right, so I'm going to use my terminal here instead of using Markdown. So over here we have 2 minus 9, which is a 3, and then this is a borrow of 1. So the 2 is still, I still call it x, and 9 I still call it y. But in this case, it is better to call the x what we call the minuend, M-U-N-I-E-N-T, or D, minuend. And then this is our subtrahend, okay? And this one here is our Q row, which is the same Q as before, okay? Now, I will call it the same Q at this point, but later on you'll see why I call it the same, okay? This is the single digit result of the subtraction. And this one, I call this row T for take, okay? So this is our row take, which is basically the borrow, but since I use B as the function name of the borrow, so when I want to name the row, I don't want to reuse the same letter, so I call this the row T for taking something away from the next column. And so this is an example how we set up a single digit subtraction. So let's go ahead and perform a multi-digit subtraction, just so that we are sure that we know how to do subtraction in base 10, but using this particular format. All right, so let's go ahead and use 192. Yeah, that will work. Minus in base 10, 289. Okay, so I think that's probably a good one to use. Okay. So we have 2 more rows here, and then we have the result down here. This is x, our minuend, and this is y, which is our subtrahend. This one here is q. Oops. And then we have another subtraction here. This is our row T, which is kind of the row of borrows. And then the last row is the actual answer that we want, which is a difference. Okay, so the difference is the end result after a subtraction that we are interested in. So now we go ahead and try to fill in all of these cells. So 2 minus 9, as we already wrote down earlier, has a single digit of 3, but it needs a borrow from the next column. This is the takeaway from digit 0. Since digit 0 is the least significant digit in this subtraction, so implicitly we have a borrow of 0 from digit 0. So now we have 3 minus 0, which has a single digit result of just a 3. Okay, so put a 3 here. All right, so moving on to the second column. The second column, or digit 1, has 9 minus 8. The single digit result of 9 minus 8 is a 1. Then we have a 1 minus a 1, which has a single digit result of 0. But in this case, neither of the subtraction, neither 9 minus 8 nor 1 minus 1 is giving me a borrow of 1. So that means we have a borrow of 0 from the next digit. And then we have 1 minus 2. 1 minus 2 has a single digit result of, I'm trying to get you guys to participate. So what is the single digit result of 1 minus 2 in base 10? 9 is correct, okay? So even though the value is -1, the way we represent it here is 9, because we are going to use the borrow to help us, take care of business. Okay, so it's a 9, and a 9 minus 0 is also a 9. So now we have an overall borrow over here, and we'll just let that borrow, the overall borrow, we're just going to let it hang around like that, okay? So now the question is, well, does this result make any sense? Because most people would think, okay, 192 minus 289 for sure is going to be a negative value. But we end up with 903, and that's not negative, okay? In fact, it is larger than any one of the numbers that we start off with. What is the problem here? We don't have a problem because we have an overall borrow of 1. Okay, let me use the mouse pointer to point to where the borrow is. So we have an overall borrow of 1 here. This 1, but this borrow is not exactly a quantity of 1. It is 1 of, guess what, 1,000, okay? So if you're thinking about this, okay, so the best way to kind of imagine this or to have a mental picture about this, okay, is, yeah, well, we can use banks, and financial institutions in this particular example. So let's just say that I have $192 in my pocket. So X is how much money Tack has in his pocket, okay? And then 289 is the bill that I have to pay, okay? So there's no way that I can defer the payment of this particular bill, okay? So what do? Well, I say I don't have enough money to pay $289 when I only have in my pocket $192. So what I ended up doing is to borrow $1,000, okay? So I borrow $1,000 from who knows, right? Some kind of bank. And as a result, after I borrow $1,000, combining that with $192 in my pocket, and then take away $289, I do have $903 in my pocket. So Tom is exactly right about that, okay? Because the actual net value, my actual net worth, is not $903. My net worth is 903 minus 1,000. So I have a negative net worth. But guess what? I did end up paying the bill, okay? It's just that, I'm now, in debt. I don't have a positive worth anymore. It sounds like student loans. Yeah, student loans are brutal. And they changed a lot. There's a lot of changes from the time when I went to college to when you guys are going to college. Because when I went to college, college was not that expensive. So the student loan that I had to take out, well, I never took out any student loan because I was actually working the whole time. But the student loan that most people have to take out is not really that much money. So most people, did not have to spend like an entire lifetime to pay off, their student loan. But you guys are living in an era where it is quite expensive to go to a university, a CSU or a UC. So I think you guys made the right choice, to start with a community college. It has nothing to do with whether you can get admitted to a CSU or UC or not. It is about saving money. Okay, if you can save 2 years of expenses, that's a good chunk of money. And Daniel was typing something, so I'm gonna wait a little bit here when I set up the next example. All right. I was expecting Daniel to have typed something, but it's not there. But that's okay. No, not a problem. So I just want to talk about notations a little bit here. So we have a rxy being the single digit result of x minus y this time, and then bxy is the borrow of x minus y. So if I want to look at a particular base, okay, so I will say for base b, how do I define rxy? That's okay. I'm not disappointed, Daniel. It takes a lot to disappoint me. Well, okay, I take it back. It takes very little for myself to disappoint myself. Well, that's not true either. Yes, try harder. All right, so we're going to go take a look at how we can define rxy. Okay, so rxy for a particular base b, okay, is actually quite easy. Okay, so what we do, there are two ways to do it. I'm going to use the easy way to. I'm going to take the easy way out. So we're going to take b, whatever b is. So if we're talking about base 10, b is 10. So we add x to b and then take y away from b. Now, if I just do it this way, okay, let me just kind of leave the equation the way it is. So if I just do this, then you can say, but Tack, what if x is greater than or equal to y? Then you end up with a single digit, quote unquote, single digit result that is not a single digit anymore. Well, yeah, I do realize that. However, if I mod it with b after that, then I'm guaranteed with a single digit. Yep, there we go. So Aiden has got it. I don't think you need to multiply b by 2 because x is a single digit. So b by itself, b plus x should be greater than or equal to y for sure. So there's no need to have a times 2. But it's okay. There's no need to say oh, because the multiplication by 2 won't ruin it either. It's just not necessary. It still works, exactly. So as long as you're multiplying b by a non-negative integer, it will still work because of the mod b. Does everybody understand why it works? Okay, so I'll give you an example after this. Okay, so we'll go ahead and define what is borrow. So borrow is actually really easy as well, because if x is less than y, then we have a borrow of 1, otherwise we have a borrow of 0. It's just that. So are we good so far? How we are defining r and b for any base. And Tom is typing. We can definitely take a look at a few specific examples. I mean, that's perfectly okay. So let's go ahead and take a look at this. Okay, so for base 10, it's having a problem because of the less than here. So I'm going to change the extension of the file to .txt so it doesn't highlight it like this. No. There we go. Okay. So it doesn't have the highlighting anymore. It's just a plain text file. All right. So for base 10, okay, let's try to figure out what is the single digit result of 2 minus 9. Okay, because we're basically reusing some of the examples that we have seen. So 2 minus 9, if you look at this, it is now 10 because 10 is our base, plus the 2, which is x, and then we take this amount and subtract 9 from it, and then we do a mod 10. So in this case, whether we mod 10 or not doesn't really matter, but in the end, we just got 3 back. When we look at b, which is the borrow of 2 minus 9, then we are looking at whether 2 is less than 9, which is the case. And because that is the case, we're returning the 1, which is our then value. So this is actually a 1, just like that. So Tom has a question, which is rxy always going to be a single digit return? Yes, so that's just my notation, so I use the r function to indicate the single digit result of addition previously, and now we're using r for the single digit result of a subtraction. But I choose to use the same name R in this case for a reason. Okay, so we'll later on see why I can use the same name R. Okay, even though for any base in general R is different. When you compare it to the addition R, but for base 2, as it turns out, it is actually the same. But I just want to make sure that everybody understands these two examples. Are we good on these two examples? We're just basically applying the definition of the general definition of R and B in base 10 and use R2 minus 9 as an example. So are we good with this? All right. Okay, cool. All right, so now what we're going to do, well, thank you for the confirmation. So what we're going to do now is to say, well, what about base 2? Well, okay, let's take a look at base 2. So when we look at base 2, Rxy, so I'm going to say specifically for base 2, okay, Rxy is just going to be kind of the same thing, right? R plus X. All right, so we take the whole thing, we subtract Y from 2 plus X, and then we say mod 2. And then for B of xy, because now we are talking about base 2, so we are actually, it doesn't really matter what base we are talking about. The borrow function is always the same, so it's just x is less than y. If it is the case, then it is going to give us a value of 1. Otherwise, it will give us a value of 0. So okay, no big surprises here, right? Because we just look at the general equation for base B, and then we just change B to 2, because now we want to look at the specific version for base 2. So are we still good? Okay. All right, cool. We got some confirmations. So assuming this is good, then we want to look at a table, okay? Because now we want to, base 2 is really easy to work with because we only got 4 cases, right? Because x can be a 0 or 1, and while x is a 0, y can be a 0 or 1. While x is a 1, y can also be a 0 or 1. So we only got 4 rows or 4 cases to think about. So now we'll go ahead and take a look at a table. So for B, you can do not x and y. Yes. So we'll get to that point. So we have x, we have y. X is our minuend, y is our subtrahend. So now we look at Rxy, and then we'll look at Bxy over here. So this is just a table. X can be 0, x can be 1. While x is 0, y can be a 0, y can be a 1. While x is, while x is 1, y can be a 0 or y can be a 1. Just like that. Caps lock. Yep. Okay, there we go. So now when we look at the R function, 0 minus 0 has a single digit of 0. When we look at the single digit of 0 minus 1, which is kind of the tricky, the tricky case, is how do we figure this out? Well, don't think, okay? Well, okay, I do encourage you guys to think in general, but in this case, there's no need to think too much, because all we need to do is to say, well, we'll put, okay, let me just point out what I'm going to do here. So we'll put a 0 here, and we'll put a 1 over here, and then we just use the definition of R to help us figure out what the answer is supposed to be, right? So we have 2 plus x, which is 2 plus 0 in this case. So that would give us a total of 2. But y is a 1, so 2 minus 1 is a 1. 1 mod 2 is a 1. Okay, so that's how we can kind of overcome the mental block of why is that why is 0 minus 1 a 1 in base 2? Okay, you can understand it from several perspectives, but this is one way to do it, is to plug in the 0 and the 1 into the R function, and then just say, oh, okay, since the R function made sense before, it still makes sense. It's just that when we substitute x with a 0 and y with a 1, then we end up with a value of 1. Okay, so it should still make sense. All right, 1 minus 0 has a single digit result of a 1, and that's pretty easy to understand. 1 minus 1 has a single digit result of a 0. So now we move on to the b, or the borrow function. 0 minus 0 has a borrow of 0 because 0 is not less than 0. 0 minus 1 has a borrow of 1. 1 minus 0 has a borrow of 0. 1 minus 1 also has a borrow of 0. So the first thing, okay, I'm hoping most of you would recognize, the first thing is, hey, this R function has the same column as the R function of addition, right? Because 0 plus 0 is 0, 0 plus 1 is a 1, 1 plus 0 is a 1, and then 1 plus 1 is the only one that has a result of a 0 as well. Or I shouldn't say the only one, but it's the other one that has a result of 0 when you look at the R function. So yeah, so indeed, the R function is identical to the one that we have already talked about in binary addition. So that's super handy, because now we can just say, oh, so that means the row Q, which is up here, when we apply, the R function to row Q for binary subtraction, is business as usual, just like last Thursday, okay? So that part has not changed. And then we look at the borrow function and go like, but this one doesn't work anymore. So this time, how are we going to define the borrow function so that the only time it is a 1 is when x is a 0 or false and y is a 1 or true. So Aiden has already pre-answered that question, so good job. Okay, so let's go ahead and take a look at what Aiden is suggesting and see whether that works or not. Okay, so we want to use the negation of x. Okay, I'm going to use extra parentheses just for this time, just so that this way we understand that the negation applies to x only and not apply to the conjunction of x and y. Okay, so I'm going to use the full notation with extra parentheses just to emphasize what the negation is applied to. So we want to look at this definition of b and ask, well, does it give us the same column? So if you look at the first row, x and y are both zeros. Okay, not 0 is a 1, but y is a 0, so we get 1 and 0, which means the end result is a 0. When we look at the second row, x is a 0 and y is a 1, so not x is not 0, which is a 1. Y is already a 1, so we have 1 and 1, which means the end result is a 1. When we look at the third row, x is a 1, not x is already a 0. I don't even need to care what y is, because if at least one side of a conjunction is a 0, the whole thing is going to be a 0. And then the last row is the same thing, because x is a 1 already, not x is going to be a 0. And we have at least the left-hand side of the conjunction being a 0, so the whole conjunction is going to be a 0. So as it turns out, we just have to make one slight modification because the carry function is just x and y, and the borrow function is negation of x and y. That's the only difference. Okay. Well, but something is still not right. Okay, it doesn't seem right to me. That it would just be that easy, right? I mean, how can things be that easy? So what we want to do now is to look at how the digits relate to each other. So we'll say Q of I is continue to be the same as the result of xi, yi. So in this case, the R function is the same as before, because we have already seen that the R function row, the R column is the same as before. So it is, you can use exclusive OR if you want to, or you can say it is not x and y or x and not y. Okay, so both of those definitions will work. But the point is, it is the same as binary addition. So now we take a look at t. Okay, so when we look at t, it is kind of the same as when we look at k. So when we look at ti plus 1, okay, then we say, well, there are two sources of borrows. Okay, when we look at the base 10 subtraction, we can see how a borrow can result from x minus y, but a borrow can also result from q minus t, which is not illustrated in this particular example, but we can see how that can happen. Okay, So now we say, okay, so one source of a borrow is coming from xi minus yi. Another source of borrow is coming from qi minus ti. So now the question is, what do I put here, okay, in between these two? Remember we had this problem, or we had this question when we were talking about carrying. So we now have the same question of, should I use just a logical OR, or should I use a real addition here? Okay, so let me make it clear what our choices are here. So the question is, should I use a real addition, like a plus here, or should I use a logical OR over here? Now my hope is that we can use a logical OR, because if I can use a logical OR combined with the way we define the borrow function, that means now we are boiling everything down to Boolean operations. And we like Boolean operations because every Boolean operation can be implemented using transistors, okay? And that's because every Boolean function or Boolean operator that we know of can boil down to NAND operations. And we already know that NAND operations can boil down to 4 transistors. A NAND 2 can boil down to 4 transistors. So it may not be the most efficient way to boil everything down to NAND first, and then we translate everything into transistors. But the point is, it is possible. Okay. At this point, I just want to know, can we use transistors to perform these operations? And as long as the answer is yes, I'm good. Okay. So do we have any questions at this point? Does everybody understand what I'm trying to ask right now? Okay, can we, instead of using the plus, can we use a logical OR? That is the question. So are we good so far, or are there questions? All right. I'm not seeing any questions in the text channel. Does anyone need more time to absorb this? Okay, I'm not seeing anything either. All right, so we'll continue. Okay, yes, more time? Or yes to continue? I guess we do end up having more time then. All right. Okay. So are we ready to go? All right. Cool. Okay. All right. So don't hesitate to let me know that you need more time. Okay. And then we'll go through a few examples, just to make sure that we do understand the concepts. Okay. All right. So we have to ask the same question, just like what we did before. A bit confusing. Okay. All right. Cool. So we'll ask the question of if bxi yi is a 1, what do we know about b of qi ti? Remember we asked a question similar to this for addition, for carrying. So we are basically asking a similar question. Okay, more explanation. Okay, so Daniel, do you have any specific thing that you want me to explain now, or you're just talking about when we need to, you will ask for more explanation? Okay, all right, cool. All right, so we are now getting down to this point here. If bxi yi is a 1, what do we know about bqi? All right, so the connection here is, so I'm going to use a kind of more or less math proof here. So if bxi yi equals to 1, the first thing we know is what? The borrow function, just like the carry function, only has one specific row being a 1. Yep, so I think Aiden is on that point. Yep, exactly. Okay. No, it's I plus 1. So this is I plus 1. Ti plus 1 depends on T of I. We cannot have T of I depending on T of I. But I'm looking at a hypothetical case here. What if the borrow of xi minus yi is a 1 already? What is that telling us? So what we need to do is to go back to the truth table and say, well, if bxy is a 1, we know for sure that this is happening. Okay, I highlighted a little bit too much, but we know this much is happening, which means we have just zeroed in to the exact value of x and y. There are no other choices. So I'm just going to type it here. So we know x of I is indeed a 0, and y of I is indeed a 1. Okay, well, how is that helping me? Well, it's helping me because of the definition of Q, right? Because Q is defined to be the R of xi, yi, okay? So in this case, if I already know that xi is a 0 and yi is a 1, then qi has to be a 1 in this case. Is that good? Is that okay so far? Because there's only one case where we have a borrow of 1. So if we say that, assuming the borrow is a 1, then we can deduce that x is a 0 and y is a 1. Nope, b does not equal to q. B depends on, b is a function and q is basically, well, you can look at q as a function itself, but q is the single digit result of x minus y. Okay, if you look at what I have typed here, is there any disconnection between the if and the then? Yes, so if we know that qi is a 1, okay, so I'm looking at Aiden's point here. So if we know that qi is a 1 already, then we know that the borrow of qi ti has to be a 0. Okay, so let me just type here, then we can talk about it. Okay, then we know the b of qi ti, which we do not know. Okay, we don't know the exact value of ti, but we know the value of qi is a 1. So we know that particular borrow will give us a 0. Is that okay? Oops, I just typed in a vi command. There we go. Yep. No. So Aiden, we don't know exactly what ti is, nor do we need to know. Because even if ti is a 1, 1 minus 1 still has a borrow of 0. Can we go through a detailed example? The answer is no. Okay, but let me explain that no. Because this is a mathematical proof, so it's not easy to use concrete values in an actual proof. So this is basically saying, all I'm trying to do is to say, if I know this side is a 1 already, can I guarantee this side to be a 0? Because if I can guarantee that, and if I can guarantee also, if this is a 1, then this has to be a 0, then I know for sure that I can use a disjunction instead of an addition, because the two sides cannot be 1s at the same time. Oh, okay. So Aiden is correct. Okay, so b of qi is guaranteed a 0. All right. How do we get the last line again? So the last line is referring to this conclusion, which is what we want to get to, and it comes straight from this, okay? Because qi is known to be a 1, So that means in the borrow function, this one, okay, let me highlight just the one part that I want. So we know that is going to be a 1. But when you look up the truth table, whenever x is a 1, the result of borrow is guaranteed a 0. So that's why we can now guarantee the b of qi is a 0, no matter what ti is, because we know qi is a 1 already. Yep, okay, very good. Yeah, this is a very similar argument, that we went through for carrying, because we need to make sure that only one side, up to one side of the operator, okay, the operator is this guy over here or this guy over here. We want to guarantee that only up to one side of the operator can be a 1 and not both sides can be 1s. That's what we want to prove. So this is 1/2 of the proof, because what we have here is basically saying if we know the left-hand side is a 1 already, it guarantees the right-hand side is a 0, which is good, but it's not enough, because we also need to work on the other argument, which is saying if we know the right-hand side is a 1, we also want to be guaranteed that the left-hand side is a 1. So that's what we're going to do next. But before we move on to that next thing, I want to make sure that everybody is good up to this point. So I think Christy is good, Dan will maybe, and Aiden is good too. So are we okay, or? Yeah, because this is not something that I can use a concrete example to illustrate, because a concrete example can only illustrate very specific examples, but it cannot prove that something cannot happen. It can only show that certain things can happen, but just because I cannot show that it cannot happen doesn't mean that it is guaranteed not to happen. Okay, what does T represent? So T is quote-unquote take. It is basically taking the place of carrying, but it is for borrowing in a subtraction. So T is used up here in the base 10 example. So that's basically just the borrow. And we typically do not write the borrow on its own row when we perform subtraction, just like we don't typically write the carry on its own row when we perform addition. But for the purposes of deriving the circuit, it is helpful to see the borrow on its own row. So T is basically just a row of borrows. There's no difference. Okay, so the idea of versus T versus B is B is a function. B is a function of, so Bxy is the borrow of x minus y. And it is applied twice, okay, on each column. And then T is a row of bits. So it really is just the overall, are we borrowing from a particular column? But there are two reasons why we might borrow from that column. Alrighty, okay. So are we ready to move on? Okay. All right, so I'm not seeing anyone asking for more time or more explanation, so we're going to move on. So the next thing we're going to do is to say, well, what if the right-hand side, okay, let me highlight the correct one. So what if the right-hand side is a 1? Then what can we say about the left-hand side? We are trying, okay, to say that if the right-hand side is a 1, then the left-hand side has got to be a 0. But we're going to have to prove it, okay? So now we say if the borrow of qi minus ti is a 1, then what do we know about the right-hand side? Well, the first thing is that it's guaranteed is now we know exactly what is qi and what is ti, because there's only one case in the truth table. When you look at the bxy column, there's only one 1 in here. So that means we know the first argument has to be a 0 and the second argument has to be a 1. So in this case, it locks down the value of qi. Qi has to be a 0, and it also locks down the value of ti. Ti has to be a 1. Is that okay? Does everybody follow this argument? Because this really is the beginning of the argument. Okay? So is everybody following this? If the borrow of qi is a 1, then we know automatically that qi is a 0 and ti is a 1. Okay, very good. But we also know how qi relates to xi, yi, right? So we can now say, since, okay, so let me just make it a little bit more complete. So since qi is a 0, then we know the following. The following is basically saying, xi is a 1 and yi is a 1, or xi is a 0 and yi is also a 0. Now, how do we know that? Well, it's all because q of I is locked down to a 0. But what exactly is q of I? Q of I is defined to be r of xi, yi. In other words, we know that r of xi, yi is a 0. So now when we look up the truth table, so we just basically want to focus on the rows where r, x, y is a 0, like the first row. So we know both the arguments to r have to be zeros. And then the other case when the r returns a value of 0 is when x, y, or when both of the arguments are 1s. So that's why we can come to the conclusion here of xi is a 1 and yi is a 1, or xi is a 0 and yi is a 0. So are we good so far? Getting to this conclusion, which is not the final conclusion that we want, but it's really just one step away from the final conclusion. So we good? All right, cool. So knowing that xi, yi are the same, okay, so you can just just say xi and yi are the same, okay. But knowing that xi, yi are the same implies the borrow of xi, yi has to be a what? Has to be a 0. Okay. So that concludes the proof of if we know the borrow of qi is a 1, that guarantees the borrow of xi, yi is a 0. But this is what we want, because now we know that the two sides of the operator, the left-hand side and the right-hand side, they cannot be 1s at the same time. Now, can they both be 0s? Yeah, but they cannot both be 1s. So only up to one side can be a 1. So that means whether we use arithmetic addition or we use logical OR wouldn't make a difference, because the case where they are both 1s does not occur. Okay, very good. Yeah, so this is actually a very similar argument that we did in binary addition, because in binary addition we also have a similar situation where we have the borrow of xi, yi and the when we have the carry of xi, yi and the carry of qi and ki in that case, remember? And we have to struggle and go like, well, it would be nice if we can use logical OR, but in order to use logical OR, we have to make sure that the two sides cannot be 1s at the same time. So that's exactly the same argument that we are encountering here, except the explanation is a little bit different, because instead of the carry function, we have the borrow function. But the objectives or the steps that we are taking are very, very similar, because we are really just trying to make sure that both sides cannot be 1s at the same time. So are we doing okay so far? Okay, so this means we can now define t of I plus 1 to be b of xi, yi, and this time we can use the logical OR for sure, because we know we don't need to use arithmetic addition. We can just use a logical OR, or the borrow of qi, ti. Now this is a big step because now we don't have an arithmetic operator anymore. We are boiling everything down to Boolean or logical operators. So we only got one more row to define, which is the row of the difference. So that one is easy, okay? D of I is really just a single digit result of Qi minus Ti. And that's it. So that is not a problem because we know the R function can be implemented using exclusive OR. So hey, it's no different compared to the sum, Si equals to the R of Qi Ki in the case of binary addition. All right, so after we define all of these terms, right? So let's go ahead and just perform a binary subtraction, just to make sure that we understand all of these concepts. So let's say we have 0, 1, 0, 1 in base 2, and we want to subtract from 0, 1, 0, 1. We want to subtract, let's see, 0, 1, 1, 1, okay? And I think that should be sufficient to illustrate the points that I need to make. All right, so we have one row here. This is our Q row. This is our T row. And then we have the D row down here. So let me go back and make sure that we label everything correctly. And there's another subtraction here. This is another half subtraction. So now we can perform, okay, let's do one more thing. Okay, this is a 0 because digit 0, the digit 0 is the least significant digit already. So no one is borrowing from digit 0. So that's why we can put T0 as a 0. We can assume T0 is a 0. So let's go ahead and work on this, okay? And I'm going to work on this in a very strange way. In other words, I'm going to work on this row by row instead of column by column. So we want to work out all the Q's first. Now, if you want to work out all the Q's first, you don't really have to work on the digits from the least significant to the most significant, because all we need to know is Q is the exclusive OR between the X and the Y, right? So it doesn't really matter, which column we choose to work on first. I mean, I can choose to work on this one first, okay? I would just work on these columns out of order, okay, just to make a point that it doesn't really matter. So Q of 1, which is where the cursor is located, is the exclusive OR between 0 and 1. So that makes this a 1. And I can now work on the most significant digit. The exclusive OR between 0 and 0 is a 0. Then I work on the least significant digit. The exclusive OR between 1 and 1 is a 0. And then we work on the last digit. The exclusive OR between 1 and 1 is also a 0 over here. Okay, now when we work on the T row, then we have to rely on, then we can only work in one direction, from least significant digit to the most significant digit. So this should remind you of the mechanism of carry rippling, except in this case it's borrow rippling, but it's the same idea. Okay, the reason why we have to do this, starting on the least significant digit and then work ourselves to the more significant digits, has to do with this equation here. So when you look at this equation, it says in order to know what is Ti plus 1, we have to first know what is T of I. And therefore, we have to work from least significant digit to most significant digit. So let's go ahead and take a look at T of 1 here. So T of 1 is asking, do we have a borrow when we have 1 minus 1? The answer is no. Or do we have a borrow when we subtract 0 from 0? The answer is no too. So we end up with a 0 over here. Now we work on T2. So T2 is asking, do we have a borrow when we subtract 1 from a 0? Okay, when we subtract y from x? The answer is yes. Okay, so we can put a 1 over here. Now when we work on T3, we're asking, do we have a borrow of 1 minus 1? The answer is no. But do we also have a borrow of 0 minus 1? The answer is yes. So now we have a 1 over here. Now when we work on t of 4, then we are asking, do we have a borrow from 0 minus 0? No. Do we have a borrow of when we have 0 minus 1? The answer is yes. So since we're performing a logical OR, that means we have a 1 over here as well. So are we doing okay so far? Figuring out all the t bits? I'm just gonna wait a little bit here until I get some confirmation one way or another. Okay, so Tom is asking, how come there's a 1 at the end of the t again? That 1, which I think Tom is referring to this one over here, means that we have an overall borrow. Not really unlike what we have in the base 10 example. So in the base 10 example, we have this overall borrow of 1 as well, which is basically saying, yes, Tech has $903 in his pocket, but his net worth is actually negative because he owes the bank $1,000, and it's the same thing. Except in this case, I'm owing the bank how much? Does anyone want to guess? Never enough. No, this is a very small and finite number in this case. In other words, how much am I borrowing from the bank? What happens if you set t0 to a 1? That usually is not the case. The only time we want to set t0 to something other than 0 itself is when we want to extend the width of a subtraction using, basically we want to chain subtractions. So the overall borrow of one subtraction becomes t0 of the next subtraction. But we'll get to it later. All right. So how much am I owing? So let's go ahead and finish this entire thing first, and then we'll see whether it makes sense or not. Okay. So now we look at the D row. So the D row can be figured out of order. As long as I have all the Q's and all the T's already, I can figure out the T digits. I can figure out all the D digits out of order, because the D digits are really just the exclusive OR between the Q and the T digits of the same column. So since I don't have to refer to an earlier column, so I can do it out of order. So I'm going to start with this one. Okay, this is D2. So D2 is the exclusive OR between 0 and 1, so it is a 1 itself. And if I want to figure out D0, it is 0 exclusive OR with 0, which is a 0. Then I can move on to D1, which is 1 exclusive OR with 0, which is a 1. Then I can work with D3, which is 0 exclusive OR with 1, which is a 1. So this is how I can figure out the answer. Okay, so the next thing we want to do is to say, but does this make any sense? Okay, in other words, we want to look at what is 0, 1, 0, 1 representing in a base that we are familiar with, okay, which is, to most people, is base 10. I hope we don't have a heptapod in our class. I mean, really, the heptapods have nothing to learn from me, trust me. We'll get to that. We'll get to the last one. And now we want to look at 0, 1, 1, 1. 0, 1, 1, 1 as a base 2 number is 1 plus 2 plus 4. And the heptapod is going to say, oh, it's 1, 0. Okay. Well, to us in base 10, it is just known as 7. Now we look at the difference. Okay, so the difference is 1, 1, 1, 0. So that means we have no 1, we have 1, 2, 1, 4, and 1, 8, right? So we have 8 plus 4 plus 2, which is 14. But the heptapod is going to say, no, it is 2, 0 in base 7. But we're going to stick with base 10 for now. All right, so this looks really odd, right? 5 minus 7 is 14. Really? So I'm going to go back and answer Christy's question, because Christy, if I understand the question correctly, is asking, what is this 1 representing? Okay, Well, let's figure out what each digit is representing. Okay, so this 0 is representing how many ones. This is representing how many twos, how many fours, how many eights. So this one here is representing how many 16s. In other words, in this case, I'm owing 16. So even though I have $16 in my pocket, I owe the bank $16. So when you look at the net between 16 in my pocket but owing a quantity of 16, I have a net of -2, which is the correct answer, right? Because 5 minus 7 has a value of -2. All right, so Tom is typing. So you borrow 16. Yes, so I borrow 16 because now I have a debt of 16. Just like in the example that we first worked on in base 10, when x is less than y, then you end up borrowing. But the question is, how much are you borrowing? That depends on what base we are working with and how many digits we are working with as well. So in this case, we're working with 4 bits, so we can only have an overall borrow of 16, or we are not borrowing. Are we okay so far in binary subtraction at this point? Okay. The t's. What about the t's? The t's are the borrows basically, but I don't want to call them borrows because I already use b, as the name of the function, so I don't want to name the row b, so I use t because take, is like borrow. Okay, how do I get them? Well, the t's are all computed using this equation here. That's how we get to all the t's. Does that make sense? All right, so this is something that you guys can do. Okay, so instead of looking at it this way, using exactly the same numbers here, you can now say, bit 0 of x is a 1, bit 1 of x is a 0, bit 2 of x is a 1, and so on. Okay, now you define all the y bits. Okay, y0 is also a 1, y1 is a 1, and so on. Okay, so we're just defining the individual bits this time. Okay, but now you apply the following so that you can actually fill in the entire equation. So now you basically look at q of I as the r function applied to xi, yi, and then you look at the t value. Okay, I'm gonna be lazy and just copy and paste. And there is where I want to copy from, and this is where I'm copying to. And then last, we have d of I defined as the r of q of I and t of I. So that's the bottom line. Okay, these are the givens. The givens are the x and the y's, and then the q can be computed based on the x and the y. The t's are a little bit more difficult because you have to use xi, yi, qi, ti, and then join it with an or. But the bottom line is, you can compute all the t's using this equation. Oh, there's one more thing. The one extra thing that we have to add here is t0 is assumed 0 in this case, because otherwise you won't be able to figure out the rest. So you have to be given t of 0 first. But after that, everything else is figured out using these equations. So does that answer your question, Daniel? And the other way, okay, to make this even more kind of graphical, we're looking at x3, x2, x. Okay, I'm not going to use brackets because it's really just a whole lot of typing. So we have x3, x2, x1, x0, okay, minus y3, y2, y1, y0. And then the next row are the q's, right? So we have q3, oops, off by 1. So we got q3, q2, oops, Q1, Q0. And then we got the t's. So with the t's, we have an overall t. So we have a t. We have a T4, T3, T2, T1, T0, which is assumed is 0. And then the last row are the difference bits. So we have D3, D3, D2, D1, and D0. That's basically the structure of how the bits relate to each other. So when we look at these are individual definitions of the bits, and then this one here is a graphical representation of how the bits relate to each other, but in a much more graphical way. Okay. So are there any questions about what we have talked about so far? Now, if you look at this and go like, well, there's a lot of similarity between what we're looking at in binary subtraction and what we talked about last week in binary addition, you are absolutely correct, okay? Both in terms of the structure and in terms of how we define the functions, there are a lot of similarity. The Q's are identical, okay? Because the Q only depends on the R function, and in base 2, the R function is identical when we compare addition to subtraction. So the only real difference is the borrow function. Okay, so we got a question here. Just to clarify, di is representing, no, di in this case refers to digit I of the difference, which is the result of a subtraction. The actual overall result of a subtraction. So d is representing difference in this case. We are not doing any binary conversion at all. All right, so Christy has a question. All right, I'm just gonna scroll to a later part of the notes here. So everything that I have talked about, really is in the notes too, except it's a little bit more concise in the notes, and it doesn't have a whole lot of examples. So we're gonna skip over to here when we are done. Okay. All right. So Christy has a question. If we were to assume that the column where it says x equals to 0, y equals to 0 was x equals to 1 and y equals to 1 instead, would T4 just equal to 0 then? Okay, so so I think Christy is talking about this column. Are you talking about this column? This is x and this is y. Okay. Well, if they are both ones, it wouldn't actually change anything. It wouldn't change the result in any way. Okay, so let me show you what I mean by that. So if we are to change this 0 to a 1 and change that 0 also to a 1, the Q is not changed because the exclusive OR 0 and 0 is of 0, but the exclusive OR of 1 and 1 is also a 0. So it wouldn't change the Q at all. And it also wouldn't change this borrow, because this borrow, or T4, is because of Q3 minus T3. It was not because of T0 minus minus Y. Excuse me. It's not because of X3 minus Y3. Okay. All right. Cool. And I know, okay, I'm guessing somebody is now going to say, okay, but Tech, if we make x3 a 0 and y3 a 1, wouldn't we end up with a case where we have two sources of a borrow contributing to this one, and this one now should be a 2? The answer is no, okay? Because if we change this x to a 0, then this becomes a 1, so we only still have one source of a borrow, and we cannot have more than one. So that's kind of go back to what we were trying to do a little bit earlier. I'm reverting this back to, because otherwise the sum is, the difference is also wrong. So I'm just using this opportunity to illustrate why we cannot have both sources of borrows being a 1, and only up to 1 can be a 1. Okay. All right. So are we okay? Let's try another example. So this time we'll go ahead and try 1, 0, 0, 0, and we'll subtract from it. Okay, we'll move the subtraction down here. So we'll subtract from this is 0, 0, 1, 1. Okay, that looks kind of interesting. And then we want to figure out what the answer is. All right. So Aiden is commenting, hey, when you subtract 1, 1, 1, 1, it just adds 1. That is correct, and it makes sense, okay? But it makes sense because 1, 1, 1, 1 actually can also represent -1. Okay, that's kind of the interesting thing. But we are not going to add to the confusion yet. Okay, so we'll stick with what we're trying to do here. There's a subtraction here and an implicit 0 down here. All right, so let's work this one out. Okay, this is the row of all the x bits. This is the row of all the y bits. Not quite. Overflow has a very definite, very specific definition. So when we get to overflow, we'll get to see what overflow really means. And trust me, to some people at least, it will add to confusion, at least at first. All right, so let's work on this one. So 0 minus 1, okay, or I should say exclusive OR, okay? 0 exclusive OR with 1 is a 1. 0 exclusive OR with 1 is a 1. 0 exclusive OR with 0 is a 0. 1 exclusive OR with 0 is a 1. Are we good so far? Because Q is really just the exclusive OR between the x and y. Are we good? All right, cool. So now we have to work on the t bits. So the t bits is the only tricky one, where we really have to go from least significant digit to the most significant digit because of the dependency of ti plus 1 on t of I. So now we look at the first column, and the first column has one borrow, which is from x minus y. So we have a borrow here, and then we work on this one, which also has a borrow because of x minus 1. So we have a 1 over here. So now we look at this one. Now x minus y does not have a borrow this time, but q minus t does. So when we look at this 0 minus this 1 over here, that gives us a borrow of 1, so we have a 1 over here. So when we look at this one here, when we look at this t bit, it's a 0, because 1 minus 0 does not have a borrow of 1. 1 minus 1 does not have a borrow of 1 either, so that's why we end up with an overall borrow of 0. Okay, great, good to know that it makes sense. But I'm going to finish the whole thing, and then we'll look at the actual value being represented by the 0s and 1s, and we also want to make sense of that. So we now have the D is really just the exclusive OR between the Q and the T. So now we have 1 being different from 0. 1 and 1 are the same. 0 and 1 are different. 1 and 1 are the same. And so now we have the actual result of the entire subtraction. So now we want to look at what value each row is representing between x, y, and d. So x in this case is representing the value of 8. Y is representing the value of 3. And d down here is representing the value of 5. All right, well, it seems to make sense. Seems to be okay. So are we okay with this? Are there any questions about the mechanism of binary subtraction? All right, so that's good. All right, so let me take a look at the time. We got 7 minutes. Okay, very good. So we still end up with a problem. Okay, the problem is just like the way I did it manually. Even though the Q can be computed all at once, okay, because we can simultaneously compute X exclusive or with Y on every column at exactly the same time. But when we get down to the T, well, there's a linear dependency because we cannot compute T1 until we know what is T0. We cannot compute T2 until we know what is T1, and so on. So now we have the same thing like what we did, the same situation that we had when we have binary addition. We have, in this case, borrow, ripple, okay? So naturally, we don't want it to happen either. So now we look at, borrow, look ahead as a mechanism. So we look at the original definition, ti plus 1 is bxiyi or bqiti. Yep, borrow, look ahead. That's what the title is for this section. So now we go through some Boolean algebra magic. Okay, and okay, it's a little bit longer than that. All right, so it's really just using the same kind of tricks that we talked about before. So I will briefly describe what happens between the rows, okay? Because the point of this class is not to prove a theorem, but it is important to me that I can prove it. So this is really just the definition. Going to the next row is based on the definition of the b function for base 2. And going from the second row to the third row, let's see, what did I do here? Oh, that's just based on the definition of qi. And then going from the third to the fourth row, it is because of De Morgan's law. So this negation that is on the outside is quote unquote now distributed over the addition, except when you apply De Morgan's law, the operator that is negated will have to change. If it was a disjunction, it becomes a conjunction. So this is the result of applying De Morgan's law. From here to here, we have De Morgan's law again, because there's a negation applied to a conjunction. There's a negation here applied to a conjunction. So once again, I applied De Morgan's law. So now we end up with this instead of this, okay? And then we end up with this instead of this, okay? And then from here to here, it is distribution. I take this thing here and then just distribute everything, so I end up with that. Okay, I think most of you call it what, FOIL, right? So FOIL also works in Boolean algebra. Now we simplify, because when we have not xi and xi, well, that's just false, because at least exactly one side of the conjunction is false, so we can know the entire conjunction is false. And the same thing applies when we have yi and not yi, so that accounts for this 0 here. And then from here to here, the zeros are basically just simplified out, because false or whatever is just whatever. So we basically just got rid of all the zeros in this case. And then from here to here, I introduce the identity of conjunction, and then I change the identity of conjunction to something that's longer and also seemingly unnecessary. And then I do a distribution, so I end up with this part over here. And then I use associative law to, I use commutative law to move things around a little bit until everything kind of aligns. Then I applied factoring, so I turned this into this, oops, and I turned that into that. So that's just factoring, which is a skill that I showed already in the case of binary addition. And then from here to here, it's another level of factoring, because we can see that not xi is common to both terms in the disjunction. So the not xi gets factored out, out of the disjunction. And then same thing happens over here because we have yi being common to both of the conjunctive terms inside a disjunction, so it gets factored out to here. Then we are left with yi or not yi, which is guaranteed to be true. Over here we are left with not xi or xi, which is also guaranteed to be true. And then the true and whatever is simplified out because true and whatever is just whatever, so the ones get simplified out. And then we look at this and we use factoring because both of these terms in a disjunction has t of I, so I factor out the t of I, and this is what is left of the disjunction, and that's the final form. Got a few comments going. Aiden asks, why does 1, which is true, equals to true or blah 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 or blah blah blah? Well, because it does. Okay, I'll use the truth table to show you. It is a or. The plus is a or. That's it. Okay, so I'm using arithmetic symbols to mean their Boolean operation. In other words, if you think about C++ programming, I'm overloading the operators. And then Dawood has a question of, can we have the code for attendance? Yes, absolutely. I was actually intending to disclose that earlier, but then I forgot. It's take, T-A-K-E, take. All right. And Tom also comments, for people on the wait list, no, there is no change at this point. In other words, no one has 3 absences as of last Friday, so I can't really add anyone to the class just yet. Now, I know that there's a deadline of adding, but as long as the dean has not told me that she would refuse to sign off petitions to add, we can still add. So, we can still kind of wait and hold on a little bit longer. So just hold on a little bit longer. When the dean announces, then I'll make a quick decision at that point to determine whether I would add people to the class or not. Oh, you have to talk to her. Her name is Kirsten Corbin. Yep. So her name is Kirsten Corbin. But as far as I know, she has not announced yet that she would refuse to sign off petitions to add. So we're still good. We can still add at this point. And I got a DM, I got a direct message. I'm just gonna check it real quick, just to make sure, but just to see whether it relates to the class or not. And Discord is super slow at this point. There we go. All right, so the question somebody else asked me, somebody in the class asked me, was if I were to give you guys a problem to solve, would we be given x, y, and t0? And the answer is, well, that would make a very easy question. So typically in a test for this class, it's going to be something a little bit more interesting. I'll give you bits kind of scattered around. So I'll give you some x, I'll give you some y, I'll give you some q, I'll give you some t, and I'll give you some d. Okay, but the bottom line is, if you know your stuff, you'll be able to figure out everything. Okay, and then the other part of this is, no, there is no calculator that I know of on the internet that can answer that type of question, which is the whole point of asking questions in that particular format, especially now that we are fully online and remote. So everything that I do in assessment is kind of by design, not Googleable. Yes, that's a word, Googleable. Oh yeah, I mean, you guys are more than welcome to build your own. If you build a tool, you can use your own tool, but I would say you do not give that tool to anyone else. So everybody can use his or her own tool, okay? But do not use somebody else's tool. If you develop it, you can use it. If you're not the developer, do not use it. All right, cool. So after this long, tedious derivation, t of I plus 1, guess what? Still depends on t of I. Okay? So now, what do we do? So now we have one little paragraph down here. Okay, so as far as as far as the test is concerned, okay, so you guys have to read the syllabus and kind of know how I look at academic integrity. So academic integrity is defined as, you know, the score of a person reflects the academic performance of that particular person. So if that person is using somebody else's tool to give me the perception of knowing the stuff in this class, but that really is not the case because it is the tool that is doing all the work and that tool is actually written by somebody else, then that person has just crossed the line and it will be considered academic dishonesty. Okay, so I just want to make it very clear before people get some idea of, hey, Daniel, what about this? You just make all the tools and we'll all buy that tool from you. So I just want to make it very clear. Not that anyone is going to try that, right? Okay, so getting back to where we are in the lecture at this point. So now what we do, this is really interesting because now we define g of I to be not xi and yi, which is this portion, right? And then we define p of I to be not xi or yi, which is this portion here. So once again, we can now say t of I plus 1 is g of I or p of I and t of I. Hey, we have seen this before, haven't we? We haven't seen exactly this using t, but we have seen something like this using k. When we talk about carry look ahead, somewhere, okay, in that discussion, we have k of I plus 1 equal to g of I or p of I, k of I. This is the same. It has exactly the same structure. So that means the overall general equation or the general expression of k of n plus 1 also can be reused for the borrow bit. So t of n plus 1 is this gigantic thing, but guess what? This gigantic thing is exactly the same as what we saw in binary addition. The only difference is all the k's got replaced by t in this case. But other than that, it's the same. So is this part okay? Okay, because this is the last part of the binary subtraction lecture, but it is also the most important because what it is telling you is the trick that we used to implement carry look ahead so that we can have a constant time carry computation can be reapplied to subtraction. Okay, so we can perform not only really fast binary addition, we can also perform really fast binary subtraction. The only difference between adding and subtracting is whether we have a negation in front of the x or not. That is the only difference. So if you build a circuit that is really generalized, like you have an independent control of whether to negate all the x bits or not, then you have a general mechanism that can be used for both binary addition or binary subtraction. You have a general mechanism for either one. And you can have one control bit just to say, am I adding this time or am I subtracting this time? All right, so that is it for the lecture. You have a lab that you have to do until you have 2 days to finish this lab. so you have to finish it by 7 p.m. on Thursday. And there's a key to that one too, so I'm going to type it here in the text channel. It is 3x3 part 1. Okay, let me just double check because I don't trust my own memory. All right, so wrong class. Yep. So this is the lab that is now open, and you have 2 days to finish this. So meaning that you don't have to rush it, but you might want to get started on this one early, like tonight, so that I will still be able to answer questions in a more interactive way. But what I'm trying to check right now is the passcode to it. The passcode is right here. So this is the access code that you need to start the lab. It is 3x3 part 1, which has nothing to do with the manga 3x3. Yeah, I'm trying to type in the text channel and it's super slow. Oh, 3x3 is a really old manga. It is actually a very old manga. I remember I was reading that manga when I was in my early teens, so I must be about 12 or 13. Oh, okay. Discord just crapped out. There we go, we're back. But I'm not sharing the screen anymore because there's no need to do it. Let me get back to the text channel, make sure that I typed that right. There we go. Yeah, Discord just crapped out. I knew it was gonna crap out because I was trying to type on the keyboard and nothing happened. Yes, we did, Andrew. Yeah, I would say so. But if you want to know it, I'll be kind and not let you know. It is okay. Let me see. What was it again? Take, Take. So you got it, Andrew? Okay, cool. All right. Well, sure. Well, good night, but I will still be online. Remember, this is the lab time of the class, which in face-to-face mode is mandatory. So I would advise you guys to try to do the lab, during the lab time. So this way you can ask me questions right away if you have any questions. Yep, the manga is called 3x3 Eyes. Okay, it's about a tribe of people who have 3 eyes instead of 2. So, all right, cool. And I'm gonna wait until Fernando and Tom finish typing. Yep, the art is actually really good. It's really unique. The storyline is actually pretty good too. All right. And Fernando is still typing. How important is it to know the proofs of tests for tests and quizzes? I will not ask you to prove, well, okay, let me take it back. I will not ask you to do the same proof as in the notes, but you will be asked in some cases to show the logic and show the reasoning of certain things. Okay, so it's not, in other words, the kind of reasoning that you have to show in the test is not quite as tedious, long, nor formal as what I have in the notes, but you will still need to know the definitions, and you will still have to be able to reason out things. So when we get to exam 1, I will give you guys what I asked in the previous semester, so you will have a very good idea of what kind of reasoning I'm expecting from those answers. All right, so I think we're good. I'm gonna get out of the voice channel and have my dinner, so I'll be back in 10 minutes. Okay, so I think you guys can probably do the same thing, and then we can get started with the lab. All right.